Hello everyone, this is Mohammed again on another session on statistics. Last session we talked about on what type of tests we need to use when we want to compare two means. This session we're gonna talk about situations or contexts where we have more than two means. So the type of test we're going to use in this context is called ANOVA, analysis of variance. So before I start talking about analysis of variance or ANOVA, I'd like to give you a very brief summary of what we talked about last session. So last session we talked about a design where we have only two means. So uh, we had parametric versions and non-parametric versions. So once a our design is a between subject design, and there are two different groups in the design. We use independent sample t-test as the parametric default version. So if the normality of distribution assumption is violated, we can use the non-parametric version, which is Mann-Whitney U-test. On the other hand, if the data are not independent from each other and they're paired and coming from the same group of participants, then we use parametric samples, paired sample t-test, which is a parametric t-test. But if again an assumption is violated, we need to use Wilcoxon signed rank test. And when it comes to t-test, we have three assumptions: the normality of this distribution, independence of the data, and homogeneity of variance. And I talked about how we could check all of those assumptions in the context of t-test in Jamovi using different types of tests and plots. So I'm not going to go over that. I just wanted to give you a brief overview of what we talked last session, and then we start talking about ANOVA. So um, let's talk about objectives of this session. Uh, you might have noticed that the more we go forward, the more complicated uh, the concepts get, but you just need to play around with the data to come to grips with the concepts. I'm not really talking about the theoretical uh, equations. I'm more talking about the practical side of a statistics. So uh, I think that you just need practice to be able to do all of it by yourself. But these are the objectives of this session. At the end of this session, you'll be able to compare uh, means of at least three different groups using between subjects ANOVA. But if you have one single group, three means, like a longitudinal study, you can use within subjects ANOVA. You will be able to use the non-parametric versions of ANOVA, and we'll go through all of that through in Jamovi, and then you'll be able to report the results at the end of this session. So these are the objectives. Okay, now comes the thorny question again. Why ANOVA? Why not t-test? I think that you already know the answer to this question. T-test is used when you only have two means. Once you have more than two means, you need to use a different set of tests, which is called ANOVA, analysis of variance. So analysis of variance, just like t-test, has two versions. One version is a between subject ANOVA, and the other one is a within subject ANOVA. Um, Let me give you an example of the same data set we have. I think we're going to work on PWA naming data set again this session. That's the main data set for this module I created. So you should have downloaded it, and then you already know what's in there. So imagine we have a we have a treatment, and then we want to see whether uh, this treatment is a successful treatment or not. We're going to work with people with aphasia, and then you kind of find three groups, like you kind of design three types of treatments, and then you put people randomly in each of the groups, and then you will have the three types of treatments. And at the end of the treatments, you ask them to name some pictures, and then you kind of compare the means of the treatments. You want to see whether the means are different or not. So this is a between subject ANOVA because you have three different groups and three different means. But how about a within subject ANOVA? Like imagine a uh, a collection of people with aphasia go through again treatment, but we want to test them three times. Once before the treatment, once after the treatment, and once like a month after treatment is over, which is kind of a delayed test. If you could see, you could easily see that these three scores are coming from the same pool of participants. It's coming from the same sample. We're not comparing three different samples. It's just one sample, but three means. So in this type of design, the independence of data is violated. So that's why we need to use a within subject ANOVA. Just like any other test, we need to go through certain steps. First, we need to state the hypothesis. So since in an ANOVA we have more than um, two means, the null hypothesis kind of states that the means of group one, two, or three, or any number of groups you have in your sample are not different. They Alternative hypothesis kind of states that at least in one pair of the groups, you kind of see a difference in the mean. This could be between like group 2 and 3, or group 1 and 2, or group like 1 and 3. So at least in one of these groups, you're gonna see a difference, or even in all of these groups. So it's a bit different from t-test in the sense that we have more means or more groups. After we have our predictions and we state the hypothesis, we set up the criterion for the alpha level, which is 0.05. We already know that. And then we bring the data to Jamovi, we run the test, but we have one additional step here compared to t-test. We need to do post-hoc comparisons because we have more than two groups or two means. We need to do post-hoc comparisons. The rationale behind post-hoc comparison is to find the differences in the pairs, like between group 1 and 3, group 1 and 2, and group 2 and 3. So we need to do other tests to find the differences among the groups. And then we report the results, and like the t-test, we need to check the assumptions. Let's see how we could run an ANOVA test between subject ANOVA in Jamovi. So our dependent variable is picture naming latency, and our independent variable is treatment, which consists of three levels. And A, B, C, each of them stands for one type of treatment. It's a categorical variable, that's our independent variable. And then we're gonna compare the means across the three groups. Our null hypothesis is that the means across the three groups are not different. And then we're gonna test that null hypothesis using ANOVA. So we started with exploration for descriptive statistics, then we worked on t-test and different types of t-tests. Now we're moving to another tab which is called ANOVA. So you click on ANOVA, again on ANOVA. So we're going to put the dependent variable here in this box, and the independent variable is treatment type, which has three levels. So um, it's it's not very difficult also once you put these things, the variables in the boxes, you kind of see the results. So the result is saying that if you look at the p-value, you kind of see that is larger than 0.05. That means that uh, we cannot reject our null hypothesis. In other words, the means across the three treatment types are not statistically different from each other. But we also have effect size for ANOVA. For any type of test, we need to report effect size. Once it's not significant, we don't really need to report effect size. But think that if it's significant, then you need to report eta squared or partial eta squared. These are two of the most popular effect sizes. And eta squared is also from 0 to 1. Once you see a significant result, that doesn't mean that the difference is the effect you're seeing is very big, and you need to have effect size to make sure how big that difference or how big that effect is, which is more about the strengths. And it ranges from 0 to 1. Closer to 1, the bigger the effect. You could see here that is almost very, very close to 0 is 0.04, which kind of is not a surprise because it wasn't significant. The result wasn't significant, and then the effect size is also very, very small. And then since we have three groups in our sample, if the results were significant, uh, we don't based on this output, based on this table, we don't really know where the differences lie, whether we have a difference between group 1 or 2, or group 1 and 3, or group 2 and 3. This table does not show anything about the comparisons across the groups. It's just showing whether the, the test itself is significant or not. So once the p-value here is significant, we move on to a post-hoc comparisons. So we see the treatment type here, which is our independent variable consisting of three levels. And then we have different types of corrections indeed, like Tukey, Chef, Bonferroni, and Holm. We select the Holm test. Uh, the idea of correction is very interesting. Since we are comparing so many levels with each other, we need to apply corrections on our p-value, because it's like going to fishing in a pond. So the more fishing rods you have, the more fish you're gonna get. And the same analogy applies here too. The more tests you're gonna do, the more significant results you're gonna get. So you need to have a correction on multiple comparisons to control for capitalization of chance effect. So that's the Holm or Bonferroni test we usually use, but here Holm is okay. So you could easily see that the difference between group A and B is not significant. The difference between group A and C is not significant. The group B and C, the difference is not also significant. So that's pretty much in line with what we got in the table here, in the ANOVA table, because the ANOVA table was not significant. So that means that there is no uh, no significant result even between the groups. So we didn't really need to proceed, but I just wanted to show you how we could do post-hoc comparisons. So that's how we basically do an ANOVA, and then and then I'll tell you how to report the test. A word on multiple comparisons and post-hoc tests. As I told you, a significant result in the ANOVA does not necessarily mean that all groups are different from each other. But it indicates that at least two groups are different. So that's the rationale behind doing multiple comparison, and that's why we are doing correction for multiple comparisons, because as I told you, the more tests, the more comparisons you do, the higher the chance and probability of finding significant effects. So that's why we need Bonferroni and Holm corrections to control uh, for this effect. Let's see how we report the results. So that's how we report the results. We have to start with some descriptive statistics for each level in the condition, which was the treatment type. We have three treatment types. We give the mean and a standard deviation for each treatment type, and then we basically say that, yeah, there was not a significant effect of treatment on picture naming among the people with aphasia. We report F and we report the p-value. Since the result is not significant, it doesn't really make any sense to report the effect size. However, if the result was significant, we needed to report both effect size and at the same time the result of the multiple comparisons. So like any other test, one way between subjects, ANOVA also uh, has its own assumptions, normality of distribution, homogeneity of variance, and independence of observations. Well, I think I talked about these three assumptions in t-test. I'm not going to talk about them again. It's just the same concept, but in a different test. Uh, in order to see whether our data have met the assumption of normality of distribution, we need to run a Shapiro-Wilk test and at the same time look at the QQ plot. So I already told you that the Shapiro-Wilk test is a test of normality. So once you look at the p-value here, you could see that it's a uh, big p-value. So that means that our data is normally distributed. This is not a surprise because once you look at the QQ plot, the dots are kind of aligned on the line over there. So our data is not suffering from normality of our data is kind of okay when it comes to normality of distribution. However, if the normality assumption is not met, you need to use a non-parametric version of one-way between subject and ANOVA, which is Kruskal-Wallis rank sum test. Is just the same. You just click on the ANOVA tab and then there comes this menu. And then from this menu, you need to select one-way ANOVA, Kruskal-Wallis, and the dependent variable is picture naming, latency, and the independent variable is the treatment type. It's just because the normality assumption was not met, we need to move on with a non-parametric test, which is Kruskal-Wallis. How about the homogeneity of variance assumption? How do we check that assumption? So to check that assumption, we need to run a Levens test. You remember that when we were talking about t-test, we also had these tests. So a Levens test tests the null hypothesis that the population variances are equal, or the uh, variances in all the levels in our group are equal. So a significant result means that the homogeneity of variance assumption is violated. Here we have a fairly big p-value, which means that the homogeneity of variance assumption is okay in this data. And if you want to do it in Jamovi, basically is there below assumption checks. You just tick homogeneity test. If you want to do normality test, you just check the normality test. and then you'll see the results. Um, what happens if the homogeneity of variance assumption is not met? Basically, again, you need to run a different test, which is Welch test. You remember, again, in t-test, we had this type of test. If the assumption was not met, we ran a Welch test. It's the same in ANOVA. So if the homogeneity of variance is violated, we need to run a Welch test. So you just go to the tab called one-way ANOVA, and then you select Welch test because equal variance is not um, assumed. And then you just run the test, and the interpretation is exactly like one-way ANOVA. We're kind of finished with one way between subject ANOVA, and then we're going to talk about one-way repeated measures ANOVA, where we have the same people in one group and we just test them more than 2 times over time, and then we want to see whether their performance is different across the 3 or even more time points. So this is a within subject design. So it's very different from between subject design. So in this case, we will use a one-way repeated measures and these are the steps we go through in order to do repeated measures ANOVA. Is exactly the same steps as between subjects ANOVA. I'm not gonna go through them. The same hypothesis, and again the same types of steps, but we'll go through them one by one. So let's do the repeated measures ANOVA in Jamovi. So what we're going to do is to uh, compare the means of anxiety before treatment, after treatment, and like 2 months after the treatment was over, which is called delayed anxiety after treatment. So we had like a group of people with aphasia, and then we measured their anxiety 3 times over time, and we wanted to see whether their anxiety changes as a function of time during treatment or not. So we click on ANOVA, we go to repeated measures ANOVA. So we have several boxes here. We'll go through each box one by one. So if we start with this box here, uh, if we kind of want to name our independent variable, or in the context of ANOVA, sometimes they call it factor. We call it time, and it consists of 3 levels: pre, post, and delayed. You could just, these are arbitrary names. You could have any name you want. And then the names kind of appear here, and then you can uh, drag your uh, levels of the factor here. So you make sure that they kind of read together: before, after, post, and delayed. So a a quick look at the result of repeated measures ANOVA indicates that, yeah, there is a significant difference between the means, because our p-value is below 0.05, is 0.001, is way smaller than 0.05. So, but a significant result here doesn't mean that all of these levels are different from each other. That just means that one pair of them could be, at least one pair of them could be different. So what we want to do, we want to do post-hoc comparisons here. We click on post-hoc comparison. We put the time here, and then we check the toolkey to home. And then we kind of see where the differences are. So um, the differences are between the pre-test and post-test, and between the post-test and delayed test. There is no significant difference between pre and delayed. So if you want to uh, have a plot, you go to estimated marginal means, you put the time here in this box, and then here you'll see a plot like this where it uh, easily shows where the differences lie. If you want to present this plot in your paper or project, you can easily do that. So you could see that before the people with aphasia started their treatment, they had a fairly high anxiety level, and then they went through the treatment. And here, after the treatment was over, their anxiety decreased. And then once they quit the treatment after like 1 or 2 months, their anxiety increased again and went almost closer to the same level before the treatment. That's what uh, we are seeing in the post hoc comparisons. And what we just need to report is an effect size to eta squared. Um, we also want to report that. So the eta squared is zero point zero 0.08 is a very small effect. I told you that the eta squared ranges from um, 0 to 1. The closer to 1, the bigger the effect. So here is very, very close to 0, which means that although we have a significant difference and we see some differences between the groups, that doesn't mean that's a big effect. Uh, 80%, only 8% of the variance in the dependent variable is accounted by the independent variable. Yeah, that's all. We'll define everything here, and then we get the results here. So, and then we look at the multiple comparisons, and then we can have graphs here. Yeah, that's all. There's only one thing, which is the assumption checks, which I will talk about it later on another video. That's how we report the results. Yeah, we basically report the main result of the ANOVA, where we saw a significant difference plus the a eta squared, which is the effect size, and then we kind of report some we kind of report where we saw the differences, which is the result of post-hoc comparisons, accompanied by a mean and standard deviation. That's how we report the results. And if we want a figure like this, we could also put this figure in the report so that our readers could better understand our results and see very easily where the differences lies among the groups or levels. Now let's see how we could check the assumptions in a repeated measures ANOVA. So we have the data here. Let's run the repeated measures ANOVA again. So we had time here, pre, post, and delay, and here, here, and here is pretty much uh, what we had in the previous video. So we want to check the one important assumption is the sphericity assumption, and it tests the assumption, the null hypothesis that the differences, the variance of the differences between groups are equal. So if this test, if the result of this test, which you can see here, test of sphericity and uh, Mauchly's test, uh, if the result is significant, then it means that the variances of the differences between groups or levels are not equal. Therefore, we need to do a correction on the F value. You see the F value here. We need to do a correction on this because this assumption is violated. And the sphericity correction we want to do is the greenhouse gaser one. See, do the once we do the correction, we'll see a new line which pops out here with some new numbers. It doesn't change the results, but anyway, it makes our analysis more robust because we just saw that the sphericity assumption was violated and we needed to have a correction on the F value, and the correction we selected was the um, greenhouse gaser uh, correction, and then we just need to update our results. We can't really present the original results because one of the assumptions was violated. That's why we need to update our results. So let's go and see how we update the results. Here are the updated results. Basically, everything is exactly the same, is very similar to the original analysis we did, but there are some differences in the um, degrees of freedom here. Originally, we reported these 2 degrees of freedom, 258, but with the new analysis, the way greenhouse gaser calculates F, it uses a different set of assumptions, so we see some differences in degrees of freedom. So we only update the degrees of freedom, which is 1.13 and 32.81. The rest of the results are exactly the same. So if the assumption is violated, the assumption of sphericity is violated, we apply a correction on the F-test, and then we update the results accordingly. We're going to talk about the non-parametric version of the one-way repeated measures ANOVA, which is called Friedman test. A Friedman test is used when the uh, one or two assumptions of the parametric one-way repeated measures ANOVA is violated. For example, when the data is no longer interval data, when, for example, the data is ordinal, you can't use a parametric test, so you need to use a non-parametric test. In this case, it could be Friedman test. And also when the normality of distribution is kind of violated, then again, you cannot use a parametric test, and the best solution is to use a Friedman test. Aside from this, the other assumptions are the same, and the interpretation of the Friedman test is just like the one-way repeated measures ANOVA. We're now going to do a Friedman test in Jamovi. So we're going to again look at the difference between 3 times of anxiety. We suppose that the data was not normally distributed, or the data now is ordinal, and then we want to do a Friedman test. It's just for the purpose of demonstration. We click on ANOVA, repeated measures ANOVA, Friedman test, and then we put the measures here. You kind of see the result here very quickly that there is a significant difference. But a significant difference does not really mean that all of the levels or groups are different from each other. So we need to do pairwise comparisons. And once we do the pairwise comparison, just like the analysis we did with repeated measures ANOVA, we only see differences in 2 pairs. And also we can have descriptive statistics plot plus a plot for the means or for the medians, which is very much similar to what we had in repeated measures ANOVA. So it means that, I mean, we're good to go. Before we end this session, let's check whether we have learned the following objectives or not. So I expect you to be able to compare means of at least 3 different groups using between subject ANOVA. I expect you to know how to compare the means of a single group over at least 3 occasions. I expect you to know what the non-parametric versions of ANOVA are and when to use them. I expect you to be able to do all of these tests in Jamovi and to be able to check the assumptions of ANOVA in Jamovi and then based on the assumption checking decide what to do next. And then I'll expect you to be able to report the result of these tests. One thing I'd like to add at the end of this presentation is that we talked about only one-way ANOVA. So one way between subject ANOVA and one way repeated measures ANOVA. One way means that we had one independent variable. So you might have several variables in your study. So you could have two-way ANOVA if you have like 2 independent variables. In our case, imagine we had a treatment with A, B, C, and then we could add like aphasia type to that and see whether the treatment would interact with aphasia type or not. So that will be a factorial design. Uh, you cannot do it with one-way ANOVA. So that's the end of this session. I hope that you like this session and please write to me. And yeah, see you soon. Bye bye.